I can either grab you a little mic, or I would say restarting the computer, one or the other.
No. Let's go as it goes.
You want to go off of there?
Yes.
Okay. And we can just leave this running. Who knows? Maybe this capturing the audio, even though it's not saying. I've had it before, where it just showed a really low level, and it kept saying that it wasn't recording, and it still did capture. Mm-hmm. So I definitely leave it running just in case. But if you want to capture it with a different one, that might help too.
Okay.
Yeah. I'll come back after your session and restart the computer and see if that was just the case. Might just be it.
Yep.
Sorry about
Thank
that.
you. So who we are and what we are doing. We are completing the sum of our courses. Which one? Quantum 2. Chem767. And the goal is to solve unsolvable. Originally declared goal is to solve unsolvable. And the there were 5 chapters in the course. Addition of angular momentum, time independent perturbation theory, time dependent perturbation theory, laser driven electronic transitions like Box here and echo, and then quantum relaxation of population, right? Would the next Thursday will be a good time for informal exam? Friday? Next Friday. Tomorrow probably, but some of us are going through Maxi exam, and it would be not good to do it before. If you set it up before, then it will give him good excuse to be less prepared for the Max.
Or the presentation. Friday, I like Friday.
Like Friday?
I'm Friday.
We can do it during group meeting.
Oh, it's Friday's your birthday.
His birthday.
Yeah,
Oh.
but,
Oh, you can show your strengths.
we have a time on this.
No, let's
like,
let's talk to your boss. If it can be merged with a group meeting. If not, we'll do like a couple of hours before. Good.
will she be there then?
What?
Will she come in?
Maybe. So, everyone is okay next Friday? Okay, good. So, we need to finish one important thing. Right now, we are going through the derivation of equation of motion for electronic degrees of freedom that will allow detailed balance principle, that would allow to describe the change of occupations in the electronic system due to energy dissipation away to the thermal bath. When we discussed possibilities, we have seen that classical path of just some degrees of freedom oscillating around will drive the system to the infinite temperature because the flows of energy in and out are equivalent. So we need quantum path. And we need to do it in the second order perturbation theory and then make a trace over the states of thermalized quantum path. Right? Last time, with a collective effort, we did open the big bracket and found all terms that come into this second order derivative expression, which was a little long. Right now, we will pick up just one term, progress all details up to the bitter end. Then I just declare how it would look like for other terms, and then by the end of the meeting, we will arrive to the detailed balance. And then I think it would be a perfect completion of the course. plus, plus, plus. Right, right, right. So, for our informal exam, Brandon angular momentum, Levi time independent, Javet time dependent elevation theory, Diane Bloch dephasing, everything from chapter 4, Aaron relaxation. So what we are doing, and some summary of everything if his schedule allows. Here are the about 20 points that we need to. Yes. You summarize chapter 4 in 3 minutes. Just give main equations and tell who needs it.
That is the example.
Yes.
No, it's not written.
No. You performed so perfectly during the semester that I don't know what you should. Well, your grade is almost guaranteed. Well, it is guaranteed. But we target not the grades. We are not kids. We since we are in this room in this course, it means that we are pursuing different goals. We are this important meeting may not be. There is a chance that it will be not recorded. My hands are busy. No, some sound is recorded, but not the in. Doesn't matter. We'll go through the material and make solutions.
No, but it's not. You could put it here.
We can, but then it will be far from the power supply.
Oh.
And I do not believe that I'm telling anything important. Most important things are out of the world. Yes, please.
I'll record it.
Thank you. So you are in this room because you select, because you are elite of the intellectual elite of the group, and because you target excellence in science. You put research as your life goal, right? Otherwise, you would not sacrifice so much of your time. So there are. We shouldn't waste much time. Just a little reminder that you all already have it in your heads. So we have simplest example of electronic system, just two level systems, and it is surrounded by bath of harmonic oscillators of different curvatures. They have bilinear coupling, and bath is in the thermal equilibrium. We are looking onto how the presence of this bath affects the equation of motion for electronic degrees of freedom. Last time we stopped at the square integral from initial time to time t dt right trace over bath degrees of freedom, and then we have sigma plus rho system time t prime sigma minus, and then conjugate. If here it was plus, then first of the for the bath operators is b without plus initiation. Bath initial, and then conjugate it to the second one should be with plus p prime. And then there are factors of phase accumulation. E to the t omega e to the power minus I t prime omega minus mu k prime plus 7 terms of the same nature having different order of these operators, right? It is what you did by collective effort by doing this kindergarten exercise of cutting and just pasting the stickers on the board. So there is a time integral here. There is average over both degrees of freedom. There is a set of system operators that include raising and lowering operator for electronic degrees of freedom and density matrix, which actually we need to propagate. And then there is a part corresponding to the path that also contain raising and lowering operators for this harmonic path. Indices should be different because we do not know which of those will be picked up for this procedure. One index from first perturbation, second index from second perturbation, and then we were using the trick of interaction feature filtering. So we put all accumulation of phase separately here, and then we will use it with time integration. What is interesting here, if you are ever planning to return them onto classical path, noisy path, then this part, phase accumulation and path operators, can be considered as autocorrelation function of the path. But now we are dissecting it into smaller pieces, and then we will apply point rules to find them explicitly. So to some extent, this portion is ACF of the path. We are done with the first one. We are 5% progress. Not yet. Trace operator surprises us and challenges us. What is it? Yes. So if you have two operators, like two matrices with two indices, if you need a trace, first we use sum over indices that are close to each other to multiply two matrices, and then we use delta function to pull out one the diagonal and sum over it. So sum of the diagonal elements, right? But what are our matrices here? What should we sum over? So we do have density operator of path, and we do have operators of the path. The trace over path will not change this operator. So you can move this symbol into here. Path density matrix is a product of the density matrix of each mode. Like if you have 1000 modes, it is a product of 1000 matrices. And each mode has only diagonal elements, and each element has decreasing value according to Boltzmann distribution. Less, and less. Right? So no off-diagonal elements, which means no coherence, and less populations according to Boltzmann and according to temperature. If you have more than one modes, they enter by different frequencies. Frequency of the mode enter into density operator of the path density. Who are those? Operators? Yes, raising and lowering for modes. If it is the same mode, you have same indices, and if different are different. You went over it in point 1. This doesn't surprise you. So in harmonic oscillator, you come from higher level to lower level by lowering operator, and you come from level M to higher level, from specific level to higher level by raising operator. So if you perform tracing over vast degrees of freedom, it means that we are making summation over indices related to operators and to indices related to each specific particular density of each mode. The highlighted black ones are those that are non-trivial, that will give something interesting. The modes for which we do not have operators will result in just one. This particular summation will give result one because they are normalized and we have a good partition function. And summation over these particular modes is given non-trivial result. For sure, done with one. What if we decide to do operation like this? B will B. It will be 0. Because the annihilation operator is off diagonal, see? Indices here are different, means it is off diagonal. And the this operator is diagonal. If we multiply them and trace, it will be 0. Same for B dagger. It will be 0. Angular brackets are not applicable here, but just by a bad memory, I will write them here and there. One should be specific and write trace. Okay. Now, what if the bath mode that has performed, that has perturbed system during the first perturbation, and bath mode that performed system during the second perturbation are different? If they are different, then we have indeed bk and bk prime. And because of the definition, it will be the same as b, p, d, k prime. So if the number index of mode is different, the average, the mean value of this operator can be replaced by product of mean values. But if we already gave an argument that first order raising and lowering operator expectation values are 0. So it will be 0. But if the indices are the same, it will be non-zero. So it means only if the first and second perturbation are coming from the same mode, then it will be non-zero inflows. So it means that we tell b k prime equals delta k prime b k. And we set up the verbal explanation of it that we are dealing with uncorrelated path. So there is no correlation between different modes. Uncorrelated path. So with this, we are done with point number 2. What is here? Oh, just writing summation over m. Let's do different indices. M minus 1. M. And then from the second operator, this summation m. And this one. This one, and then we also have the summation over n, and then Boltzmann factor. What do we see here? we do see that there are pairs of bra and cat in corresponding summations that are merging together according to the rule of anaconda and the rabbit. The snake eats the delta, the summation sign removes delta function, and we get one index less. So we can get rid of this and this, which will be delta m prime comma m plus 1. We get rid of this summation, and then we need to replace m prime to m plus 1 everywhere where it appears. So it will be summation m. Instead of m prime, we put m plus 1. Here we have m prime minus 1 will be m plus 1 minus 1, which will be equals to m. Then we have another m plus 1 from there, m here, and then we didn't touch the density operator of the bus. Huh?
You have another delta?
We will have another delta. Yes, that's correct. But what is important here? These two square roots merge together, and we are getting here summation m, square root, not square root, just m plus 1. M, 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 and it's minus. And when we, before we, as Levi has suggested, we identify that there is another delta that will have together this another symbol, and we remove the index m and replace it with the n. So m is replaced by n everywhere. And then we will have summation over n plus 1. And when we add one more delta to pursue this was just a method. If we need to find the diagonal elements, then this cat and bra will be removed, and we will have summation of the Boltzmann factor and n plus 1 here is important, that there is n everywhere in here. So if we perform this summation, we will get n plus 1, where here letter n is not indexed anymore. Right now it is Bose-Einstein distribution evaluated at the frequency of this mode. Right? And this is very simple exercise. We can do it if we have more time. Then, so n of is what? How do we recall? How does Bose-Einstein work? 1 in the nominator, exponential plus or minus in the denominator, plus h bar kt, plus or minus, minus, right? So if we plug in time equals 0, then the distribution, temperature. So T capital is temperature. If you set up temperature, there was a Japanese scientist, Matsubara, who told that time and temperature are equivalent up to imaginary constant, because both of them are coming into the power of exponential. There is a Matsuburg theory where one expansion in time replaces by expansion in temperature. It will be 1 over what? Infinity? 0. So the meaning is how many quanta are stored in the small at a given temperature. If kT is equal to the frequency, then number will be 1 divided by E minus 1. So about 2/3 or something a little less than 1. And if time is, if temperature is equal infinity, then this number of quanta will be also infinity. Right? We just recalling the Bose-Einstein distribution. We, in our progress list, we are 4 points forward, so it's about 20% done. I'm going to make screenshots and then erase everything except the many thanks to Jared for making shots and sharing. Oh. Just was a little busy time, but I plan to process them and share with everyone with some cutting pieces and comments, hopefully. Which force? Quantum force?
No. Yeah, so words. It's
I know.
fourth.
Wait, the force do you need? That's good.
Doesn't seem so words. I've heard in your life.
We should sit together, project on the bigger screen. During the weekend, go to the biggest presentation room in the department.
Like 209.
Yes. And
You're
plug
not
in
this
the
law.
computer and watch.
You're not a nerd.
So I'm going to erase everything except the first line here. And then we are going to simplify, and then we will get a digital balance at the end. We still have chances to get it. Okay. Any questions while I'm doing or objections?
So this is N of mu sub k plus 1.
Yes.
Okay. We don't have to go through it. I'll trust you. Did we do it?
So when we were doing our kindergarten exercise of big stickers, you remember that B and B dagger operators were coming in different order. When it is B dagger times B, it will be N. When it is B times B dagger, it will be N plus 1. And this is critically important thing. This is the key of everything. It is the reason why we will get detailed balance.
Yeah.
So the difference between B dagger and
B and B.
yes, it will be responsible for different amount of energy flowing to the system and from the system if it is away from the equilibrium. When it equilibrates, then it will be no flow, steady state. So what do we need? Trace over each wall. I don't remember what I was meaning, but and here you have the delta k prime. Here we have n of mu k plus 1, and here we have unchanged phase factor. Et minus mu k, E minus it prime, omega minus mu k prime. And from the trace, we still have left over by that we need to make summation over those modes that did contribute to this perturbation. So we do need to make summation over the modes. And this data function comes from our assumption, approximation of uncorrelated path. This came from the so if you perform summation over k prime, then we apply again the rule of Anaconda and Rabbit, and the k prime index is replaced by k everywhere. K prime is replaced by k. System has the value of time t minus 1 over square, summation over path nodes, integral initial time, current time, d prime, sigma plus low system t prime, sigma minus, no delta, n of mu k plus 1, e to the power I t omega minus mu k, e to the power minus it prime, omega minus mu k. So it was k prime and now is mu k. This is the plus 7, not as a number, but 7 other terms. What is good? Huh? What? Yes, correct. You have strange things on the screen. I don't know if it is yet recorded. No? Maybe. So exponentials, as Levi told to us, can be simplified how? E as I t minus t prime, omega minus mu k. Good? So by now, we already did some wrap-up operations, but we still explicitly consider contributions from each phonon mode, each normal mode, each nuclear degree of freedom in the path. Right? We make summation, like it goes to 3 and minus 6, where n is number of atoms. If it is like a continuous mode. Huh?
Non-linear.
What is non-linear? Here, linear oscillation, harmonic. There is no non-linearity. Let's do just one simple thing in the meantime. Bring at least something to the end. So we are going to make this summation. And we are going to merge this summation with this exponential and replace sum with the integral. Why? Because we want to make everything simple, and we know that integration of exponential has ability, has the potential to generate delta function. So and now we use this sum is replaced by integral. What will be our integration variable? We want to go over all modes, but we can, instead of counting them, mode number 1, mode number 2, if there are 10,000 modes, too much. We can describe the modes by VDOS, vibrational density of states. You can tell just per unit interval we have so many density of states, and the integral is replaced by density of modes at given frequency, and we do d of omega minus mu k. So this will be our integration variable. So if the frequency of normal mode is in the exact resonance with the frequency of the system, then our integration variable will be 0. If it goes higher or lower, it will be non-zero value. So we go from minus delta to plus delta. And later on, we can even do limit of delta goes to infinity if you want to. So the summation sign is replaced by this thing. There is also one term that I'm forgetting always, but it is not one cannot forgive me. One needs coupling. So we have operators corresponding to system or operators corresponding to bus, and we need the coupling strengths. So here we need G sub K, G sub K prime, where this G sub K is either transition dipole time times phase strengths, or it is not like coupling if we are talking about normal modes, about phonon modes. So always here G, K, G, K prime. And upon this summation, it will be G, K absolute value squared. G, and instead of K, also will depend on the frequency. So coupling between our system of interest and normal mode of a given frequency. So we are counting the both modes not by index, just by their frequency. Okay, and the rest is coming from here. Times n, use just this frequency plus 1, times e I times t prime, minus k. So in case delta is small, and we are very close to resonance, then those coupling in n can be placed in front of the integration. Or small delta. And then I think we are going quicker than originally planned. So trace for each mode, yes. Sum over all mode, yes. Sum goes into integral. So 7 times, we are 35% progress. Okay. D, dt, is of t, minus 1 equals 4. initial time 20 prime. And then we trace everything that depends on omega. Density of states, density of modes, at frequency omega, the coupling square at frequency omega, and number of quanta in the harmonic mode evaluated at frequency omega plus 1. And then here we have integral limit, integral minus delta plus delta, d omega minus nu sub k, e to the power I t minus t prime, omega minus nu k. We know that integral of exponential is exponential. It is especially simple if the power of exponential and integration variable are the same. We shouldn't be shy. We should be guests of ourselves and have any flavor we want. So let's make the integration variable equal to the power of exponential. So I'm going to multiply by I t minus t prime here, and divide by I t minus t prime there. Right? I'm going to switch to different panel. Density of both modes coupling square. So you see, it's getting very similar to Fermi-Golden rule, right? Times. Actually, we have exponential 1 over I t minus t prime that comes from denominator, because our trick is very integration variable, and then we have just function itself. T minus t prime omega minus nu k, where omega minus nu k changes from minus delta to plus delta. Right? So we can replace this one by e to the power I t minus t prime delta minus e I t minus t prime. There's minus here, so times delta. E t minus t prime. How do we simplify it? How do we name this function?
Simple.
Yes. Why?
Since it's number 8.
But you are educated enough, you're long enough in graduate school to know it without looking at number 8.
I'm long enough in graduate school to look at number 8.
So, what's the name of a blind mathematician who told us how to convert exponential into...
Euler.
Yes, Euler.
I didn't know that he was blind.
He was blind and he migrated from Germany to Russia. I don't know, is it good or bad, but it's like... And he was still writing his manuscript, but like stylus on the marks.
He went from Germany to Russia?
Mm-hmm.
Does the reason is like me?
No. In the last half of 18th century, there was a program of support talented immigrants, and it was monetarily beneficial. Okay, so according to Euler, we take this imaginary unit, we take this two factor, and we tell that it is a sine of t minus t prime times delta. Correct? And this will be t minus t prime times 2. And all of this, the rest, see, it looks very short now. Much shorter than you were doing before. So how does this function look like? So t minus t prime times delta should be equal n pi, or n integer number. 0. Oh, but we better do t minus t prime equals n pi divided by delta. Pi divided by delta, 2 pi divided by delta, minus pi divided by delta. And sine will go this way, right? And if you divide it by difference, t minus t prime, it will go to it will go higher, the cancel discontinuity, 0 divided by 0 in this point, and then, so the function will not cancel 0 here, and then it will be still in this way. So the width here is 2 pi over delta. And in the limit of delta goes to infinity, the width, which is 2 pi over delta, is equal to 0. So this sinc function can be considered as very good approximation of delta function, delta of t minus t prime. Okay? So all this factor, the red factor, can be replaced by delta function of time difference. So what do we have now? d dt rho s of t minus bar squared, initial time, final time, dt prime, density of omega g squared of omega n omega plus 1 times delta of t minus t prime. Good. What do I miss? You know the proverb, like, no, it's not the proverb. But by doing careful operation of all tiny step, we miss the leading term. Who wants to find the error? What is missing? The key factor is missing, most important thing. Starting from here. Yes, it was at this point, and it was missing here. So we need to have rho s of t prime, rho s of t prime, rho s of t prime, rho s of t prime.
Then you use the equation
And creation and manipulation period. Sigma plus sigma minus sigma plus sigma minus. Good. Now we are doing much better. Thank you for finding the second part.
You forgot the V2.
What?
You just did down.
Oh, okay. If it is not vibration, it will be the freedom, but modes of optical resonating bus and that will be the one. This mathematical approach is very general. V is, since we are most of us dealing with chemistry, dose of normal modes of nuclei is most appropriate. But it's completely this same mathematical procedure can be applied to different styles, different physical nature of system and path. It's a very general, fundamental approach. Okay. What is the definition of delta function? Huh?
F is equal to 1.
So by multiplying function with one argument, by delta function integrating, we are getting value of function at selected argument, right? So if we perform this integration, the integration and Dirac delta performed same way as snake and rabbit. They disintegrate and we don't have this two times linear. So we are getting d dt plus of t minus 1 over h bar squared. No integral anymore. V equals omega coupling squared n plus 1 times sigma plus rho at time t sigma minus plus 7. Where 7 is not a number but 7 other terms. We may combine together this part, which looks very similar to Fermi's golden rule, and call it capital gamma over 2. Well, we can call it anything we like. But if you the rate of relaxation, we are almost done, except that we need to do tricks with the operators and see how the order of the density operator and raising lowering operators affect the flow of direction of energy, dissipation or thermal excitation. So this will be gamma over 2, and then our equation is d dt rho time t minus gamma. Well, let's call gamma over 2 everything except this n factor, because it will be different for different orders of those. Gamma over 2, n plus 1, sigma plus rho s time t sigma minus s. We are very close. Let's count how far we are. So we are done with sync becoming Dirac delta. We defined relaxation. Oh no, we are exactly at the half. I guarantee we will be ready before 2.
Okay, you presented today?
What's tomorrow?
Huh?
What's tomorrow?
Your presentation?
Oh, for MT, yeah. I'm mostly done with it.
Oh, Scott Lyons emailed us saying you should go with these presentations.
Okay. If they are recording, then we have a chance. If they don't, presentations that are not good right now.
No, tomorrow
Tomorrow.
at 5 to 8 or
Okay.
something.
So let's take a screen.
Oh, 5 to 8:30. We'll take a 15-minute break. I'm late.
Is it possible?
Yeah.
Is possible.
Let's take screenshots and then go for the rest of the program.
There's 12 presentations, 15 minutes apiece, with a 15-minute break.
In which class? Oh, by Katsikopan.
Yeah.
Okay. So, what are we doing? We do have our very brief result, which is in the box and ends by +7. And now we need to write the rest of +7 terms, which is nothing for brave you, because you did much longer 8 terms, 16 terms in the previous meeting. And now we do not have all this long history. It looks much shorter. So let me keep maybe only the starting point, DBT. Sigma plus rho sigma minus. So let's populate these spots with the 8 terms that we derived from last time. They always, the terms that you placed on the board by stickers were always, did always have the no, it is not here. I think rho should be here. Yes. So this sequence was always plus minus for annihilation operators. And here it was minus, plus, minus, plus, minus, plus. But the difference is only where we place the rho in respect to those and the sign of the term. So here we have plus, rho. In the second row, we have minus and rho in the middle, minus and rho in the middle. Here, actually, we don't need to write this one. We can do 2 and 2. And here we have again plus, but rho goes up front.
What about your n+1?
I'm so pleased that someone is following. So the n+1 or simply n depends, which factor, n or n+1, depends on the order of operators. Because when we, for each term, the order of the system operators determines the order of bus operators when we take the trace. So for the first term, it was...
Isn't the n+1 term absorbed in that gamma over 2? No.
No. Let's put it separately. Otherwise, we will screw up everything and we do nothing. It will be same result as in the classical path.
Okay, so you.
No. It's bracket is here.
Oh.
So conjugate to this will be B. Conjugate to this will be B dagger and then roll path. And we agreed that upon average it will be n plus 1. And actually we need not angular but trace B. Okay? Nothing new. Now how it projects to the rest of things. What will be the factor in the second term? So it will be, yes, correct. So we're, because of conjugation, we have B dagger, B, trace, equals n. Good. Now, but this is, okay, simple. There is a little tricky thing with the middle row. So according to conjugation, for the middle row, we will have B, density of path, B dagger. Trace. What will be the answer? This is a perfect place to make a mistake. And almost the last chance to scroll up the world of students. N or n plus 1? Make a guess. Being so. Huh?
I say N. I say.
Any other options? You agree? Or do you disagree with DM?
I think n minus 1.
I would have said 0, but I was obviously wrong.
So DM thought that he's long enough in graduate school to read the plan. So under the sign of the trace, one can swap the order in a cyclic manner without changing the result. So this will be equal to the trace B, B, B. So yes. And then for the here term here, trace B dagger row B. It's very confusing because in this record B dagger comes earlier than B. But if you do the cyclic permutation, it will be trace B dagger row and it will result in this one. Okay? And for the last row, trace row B dagger. This goes here, this goes first. Trace B dagger row equals n plus 1, right? And for the last one, trace row B dagger B, n, right? Correct? So most highest responsibility, the most important thing for the last three students, distribute factors n or n plus 1 into these recordings. Here n, here n plus 1. Here it was n, it was n plus 1. Correct? Here n plus 1. And here n. Congratulations. You've got the right answer. could be. Now we've got the answer. This is correct equation, quantum master equation for alternative degrees of freedom, and we just need to analyze it to have some take-home message. Otherwise, we'll have only feelings of upset. We spend so much time and got just equation. How do we what happens? How do we apply it to the real life? But in fact, this is good and correct. From now on, we need just to analyze it. This, and the analysis is much simpler than the revision. So we listed all its terms, we did cycle permutation, and we did plug in n and n plus 1 terms. I am going to erase this board and so what is our major upset by looking at this equation right now, even if we believe that it is correct? It is still too long. If we want to memorize it and surprise our friends by the ability to produce this equation without a cheat sheet, we should simplify it to a little more shorthand form. So we see that time sigma plus times let's write it once again. And everything that relates to n plus 1. Sigma minus rho minus 2. Sigma minus rho sigma plus and here sigma plus rho sigma plus sigma minus. It's n, and now we are having sigma minus sigma plus rho minus 2 sigma plus rho sigma minus plus rho sigma minus sigma plus. Correct? It would be very pity to make her so close to like 20 minutes before the end of the course. Now we can identify that here we have a factor sigma minus times rho and sigma plus just in different order. So we can write this one, and here in this bracket we can write sigma plus comma sigma minus rho. Just commutator of these two factors. And then from the second part we can identify that sigma times rho times sigma plus and sigma minus also coming in the commutation order. Rho sigma plus rho sigma minus. And we can do the same trick for, so first term corresponds to relaxation. The amount of energy, well, we didn't prove that it is relaxation, but this flow of energy is more intense than this one, right? It is always bigger by 1, which is especially well pronounced if temperature is 0. Then this channel of dissipation is active and this is disabled. So the second channel that we will discover in a couple of minutes, that it will be thermal activation, has the sigma minus comma sigma plus rho bracket plus here rho sigma minus comma sigma plus. This is simple enough equation that is you can try to practice memorizing if you plan to deal with quantum relaxation after you exit the classroom. So, 4 commutators, plus minus, minus plus, minus plus, for relaxation and for thermal activation. On your place, I will be still upset. How do these commutators relate to real life? Give me something solid that can be useful. So we are already 13, and we need to write down actual equations of motion for occupation of the levels. So from operators, from density operator and raising moment operators, we need to go to functions, to occupations. And we are going to do it immediately. Let's agree that our ground will be called A, our excited will be called B, and then sigma plus will be going from A to B, sigma minus will be going from B to A, sigma plus sigma minus will be B, A, B. Plus this one will be projector onto state B, and sigma minus sigma plus will be B equals projector onto the state B. Do you need any comments or just natural? DM doesn't need comments. Right? This notation is natural. I see for you also. Natural. What have we done? Spin, we call spin weather operators. Now we are going to look for occupation of the excited state. Rho B. If you take matrix element of density operator in the state, in the excited state, as Brian had, from operator you get to the function. So it will be function of t. And for this function of rho B function of t, we can write down the equation of motion. If you would be too interested in all the details, you could do it for each of them, but for occupation of excited, it will be enough. We'll do it and then we'll stop if you've given us enough food for thought. So, I'm returning back to this notation and quickly running down minus 1 over 2 plus 1, and then I'm putting B, and then all this term sigma minus is replaced by, let me use different color. Sigma minus is replaced by BA. Sigma plus sigma minus, we can immediately write BB. Correct? Then we write rho, and then we write B because we are looking for matrix element. So we've done this first term, minus 2. B, sigma minus is A, B, then we have rho, and then sigma plus is B A. And then we have another B because we did matrix element in bracket. And yes, it will be 0, right? And then we have plus in B rho, and then we have sigma plus sigma minus, which will be B B. Then we have another B because of the bracket. Any errors found here by now? No? Okay, let's do the second row for thermal activation. Minus gamma over 2 times n. B. So we are looking at this term. Sigma minus sigma plus will be A times rho times hat of B. This one 0, yes. Next one minus 2 B sigma plus is B then rho, then sigma minus is AB, and then another B because we need matrix. And then plus B times rho times sigma minus sigma plus, which will be so anywhere where bra and cat are not equal, we will get 0 term, correct? So here we have B times A, which means the whole term will be 0. Here we have B times A, which means this term will be also equal 0. And here the last term also has A times B, which means the whole term will be 0. Make sense? And there, this B times B bracket will give 1. Here it will be also 1. And here also 1 and 1. And this bra, A bra rho A cat will be rho A A, which is occupation of the ground state. So let's continue in the little box here. D dt rho B minus gamma over 2 and plus 1. Rho B times 2. Right? Correct? So from the first line we have rho BB from here and rho BB there. Minus gamma over 2 times n. Another minus here, which will give the rho plus 2 rho AB. The factors 2 will cancel, so you just set up the notation for the rate so that it will cancel here. And then d dt rho dB equals minus gamma n plus 1 rho dB plus gamma times n rho dB. We do not need to repeat all this long path in order to get equation for rho AA, because we know that rho AA plus rho BB, the total occupation is 1, and d dt of occupation of state 1 and state 2 equals what? 0. So if we want to do dt of rho AA, we just swap the sign. Plus gamma n plus 1 rho b minus gamma n rho b. We are very close to completion. So we have equation of motion in matrix elements, and we have set of equations for population dynamics. We skip the equations for off-diagonal elements because you see they are not coupled to equations for population dynamics. If our bus doesn't have memory, if all applications that we've made are correct, then dynamics of off-diagonal and diagonal elements are decoupled. So we are free to pursue only diagonal elements, only populations. 60 times 5. Huh? 80% done? We are very, very close to completion. Right now, we have the sweetest part. That is simple analysis of these balance equations. So what do we have next? Limits in time equals 0 and time equals infinity. Rho AA, rho B equals what do we have in this relaxation matrix? For correct? Or
Plus gamma n minus gamma n plus 1 in the top row. No, I think that's right. Oh no, wait, sorry, yeah, that's right. Sorry, I thought. Yeah.
okay, so minus on the diagonal.
Yeah, yeah.
So the population of each decreases according to its proportion to its own population. Temperature equals 0. N equals 0. 2 limits. Temperature equals infinity. N is much bigger than 1. Therefore, n plus 1 is equal to n. So in this case,
Is there a mistake in that equation?
which one?
For ddt rho AA, the equation in black under the equation in blue.
No, like why?
N plus 1 rho AA.
It the rho AA gets depleted because of thermal excitation to higher level and accumulates more population because of relaxation from excited state.
Oh, so that's right. Okay.
So in case of zero temperature, we have nothing in these two rows, in this column. 0, 0, gamma, minus gamma. Rho, AA, rho, EB. Right? So I think that this is most practical equation in the whole course. It is simple enough, and it makes connection to other courses like first order chemical reaction. This is one of the differential equations that you can quickly solve. The proportional to the occupation, no quadratic terms, and it just goes from state B to state A. Right? You see connection. Good, very good. How do we solve this equation? In the limit, time goes to infinity. If time goes to infinity, we assume that solution approaches steady state, approaches equilibrium, which means that infinite time, there will be no time dependence. So the time derivative will be equal to 0. So we're at 0, 0 equals 0 gamma, 0 minus gamma, rho EB, rho EB. So it is a standard way to find steady state. Bless you. That's good. I'm trying to finish everything in a few seconds. So, if we open brackets here, we will get gamma times rho by pole, gamma plus gamma times rho dt equals 0, and at the same time minus gamma times rho dB equals 0. So it is a coupled set of equations, which means, and gamma is not equal to 0. So here is the mathematical logic. Gamma is positive and not equal to 0. Then logically it can be maintained only in case if rho dB is equal to 0. Right? Right? So rho dB at time equals infinity equals 0. And rho AA equals 1 minus rho dB equals 1. So at time equals infinity, 100% of occupation will go to the ground level. Finally, we proved something useful for the level. It is a little trivial, you all expected it, but now we go through very advanced quantum graph theory. That everything will relax down to the ground state at 0 temperature. Good achievement. What do we get in the limit of infinite temperature? So we can use n plus either n or n plus 1 in both cases, because 1 can be dropped in comparison to n. Minus gamma n plus gamma n plus gamma n minus gamma n. Which means that the flow, in this case, the flow of energy downwards was infinitely times bigger than upwards. Here they are equal. And if you do the steady state, you can just skip the step. Rho AA at time equals infinity will be 0.5, and rho dB at t equals infinity will be also 0.5. So this solution approaches us to the center of Bloch's theory. 50-50 occupation of ground and etc. We have done limits, time equals 0 and time equals infinity. And you did steady state. What is left? The thing that I was promising for like a month. So you do have process down going with intensity n plus 1 and going up with intensity n. Right? Let's look for their ratio. How much the transition up is more or less probable than transition down. So we cancel. It doesn't depend on the value of the coupling and overall intensity. It depends only on temperature. And we do have this one. This one plus 1. So what do we do if we need to solve it? Probably here we need to set up a common denominator. Minus 1 times 1 divided by exponential h bar omega pt minus 1. And here we are multiplying numerator and denominator by the same number. So e h bar omega divided by pt minus 1. Good? Yes, we can flip. This means the same as we would place denominator of denominator into denominator. Although it is very simple, I better repeat it by calligraphy once again. H bar omega kt minus 1 e h bar omega kt minus 1. And here there is 1 plus exponential h bar omega by pt minus 1. So you have 1 plus something minus 1. 1 is cancelled. And here, this denominator here and numerator there are the same. You can cancel them too. Equal to the e minus h bar omega divided by Boltzmann constant t. Boltzmann. So the intensity of transitions of thermal excitations are Boltzmann factor less efficient than thermal activated relaxation. Thermal phonon assisted excitation is Boltzmann factor less intense than thermal phonon assisted relaxation. Relaxation. How can we summarize this verbal formula into 2 words?
Two words.
Yes.
Detailed balance.
Yes. Perfect. where did you met detailed balance first? In which course or which area of knowledge?
Number 19.
No, you had it before in some like thermodynamics.
No. In Scotland, it's called for.
You didn't saw it in statistical mechanics or thermodynamics? In introductory chemistry, like Chem 150? No? Is it the like? I thought you've heard it many times in your life. So I'm just the second who tells you about detailed balance. Oh, good.
Actually,
Then-
third or fourth.
Okay, still big order. So by now you are certified experts in detailed balance theory from very background atomistic ab initio derivations. We came in some very reasonable approximations. We came to the principle that governs most of the processes in the time resolved phenomenon. As soon as we, well, on a very short femtosecond scale, there is a dynamics without relaxation, but as soon as we go longer for, let's say, 20 femtoseconds, everything goes through relaxational processes and everything follows this detailed balance. So this relatively universal principle that can be shamelessly applied to almost any model. And if your model has more than 2 levels, you just do the same for each pair of levels. You do not have time to go n level system, but general principles will be the same.
Or is it called an ad hoc approach? Or is that?
No. Ad hoc is, right now, we used first principle. So we, there is a control of approximations. We didn't, we had a chance to set up all the relations either exactly or with an approximation that we can keep or neglect. So it's very well paved way. We never jumped over obstacle until someone else will explain how to do it. We did a good, fair job of going step by step. And there are reasons to believe that it is correct, independent of implementations and the physical system where it is applied to. So we are not as strict and rigorous as mathematicians. We didn't prove, but we carefully shown logical step by step the relation. So even if some experiments or some calculations contradicted, we better believe this approach because we see the logic. Because in some random, not backgrounded experiment or calculation, especially computation, there is a chance of human error or numerical error. And here it is median line that we can use as a reference point. I look forward to your summary of the whole course in a week from now. Thank you much for being so dedicated and staying up to the last meeting. We have just one informal meeting with summary of the course, and that's it. Have a success on all of your exams. Have a nice summer and see you many times on occasions related to research. Last lecture of quantum chemistry 2, Chem 767 is done. Everyone, meeting is dismissed. You are free to either leave or stop by and ask questions.
Yeah, it already passed.
No,
No,
it says here households now on the bottom of the field.
I've got like 14 messages.
And 24 and 27 minutes. This is the Washington Post. On the Wall Street Journal.
Okay, we'll see how that's
Question
how long it feels.
for the small system that you gave me, I did 10 angstroms around. Is that
What
big
do you
enough?
mean 10 times?
You know how there was
Oh
distance?
yes, 10 is a lot.
Okay.
This should, if there are